Hello. In this video lecture, I will be covering Chapter 7, and the subject of the chapter is work and energy. Up until this point, we have been covering forces, where we said that the force is equal to the mass times the acceleration, and if the body is at rest, then the sum of the forces are equal to 0. And we were dealing with systems where either those systems are in motion or they were in a static situation. In this chapter, we will be dealing with similar dynamical system, except that we will be using another method of solving the same problem, and that is the method of energy, work and energy. So let me go into the subject of work and energy before we start doing problems. Work and energy. We define the word work, which has the symbol capital W, to be equal to the force times the displacement, or the distance, okay? I'm going to use the symbol S for now. This is what your book uses, but we can also change it to something else. So here, S is the displacement, and of course F is the force. Okay? Now, work is a type of energy. Type of energy. Let me explain what that means. Let's say, for example, there is a box. Let's say it's sitting on the floor like that. Here is the floor. And let's say if I am marking the floor with some kind of calibration, let's assume that the box is at position, let's call it x equals 0. Okay? And let's say that I would pull the box horizontally with a rope or something, with a force equal to some value, and now the box, I have displaced the box from x equals 0 to, say, this position here. Okay? And let's say x equals, let's pick a number. Let's say 10 meters, for example. Okay? So the box has moved a distance 10 meters. Okay? We define the work. So what I have done here, if you think about it, I have pushed the box to go from x equals 0 to x equals 10. So I have expended some energy, correct? You know, when I push a car to get the car to start, I will be expending energy to do that. Well, that's expenditure of energy is one way to think about it is the work that I have done. Okay? So we define the work to be equal to the force that is being exerted on the box multiplied by the distance x in this case. Or shall we, let me write it as delta x for now, because it's a displacement. So that means if the force is F and delta x in this case will be 10 minus 0, correct? You know, x, F times x final minus x initial, where this is x final and this is x initial, instead of saying. So the displacement means the distance, the difference between the two positions. So that will give me that. Now, if we say that the force, let's say I used, 10 Newton to push the box. So in this case, the work will be equal to the force, which is 10, times 10 minus 1, excuse me, 10 minus 0, and that will give me a value of 100. 100 what? Well, let's see. We said that the work, go back here, the work is equal to force times distance. So in terms of unit, that's Newton times meters, correct? Well, what is Newton and meter? Well, we refer to it as the joule. Okay, the joule is a unit of energy, instead of saying. So we can call it joules, 100 joules, and the symbol of the joule is capital letter J, so it becomes 100 J. Get that? All right. Now, there is an important condition that we must keep in mind when we calculate work. And this condition is that when I push this box, let me go back to the box. Here is the force, right? Here is the force. And here is the distance. Notice that the distance and the force are parallel to each other. In other words, the force must be parallel to the distance. This is very important. In other words, if I have a box, let's go back to the same box problem. If I have a box, here is the floor, and let's say I'm pushing, let's say I'm pushing the box or pulling it with a force in this direction, okay? And there is an angle theta here, okay? And let's say the box goes from here to there, you know, whatever distance here. The box now is here, okay? Let's call that distance x. So the work done here is basically only the component of the force, that is parallel with the displacement. Well, which component is parallel with the displacement? Is this one. Let me use a different color. Is this one right here. See that? See, there are two components here. One, the vertical component, which is f sine theta, and the horizontal component, f cosine theta. The one that is actually doing work is the one that is always parallel with the displacement. So it is f cosine theta is parallel to the displacement x, and therefore this is the one that is doing work. This one is not doing any work at all. You get that? So it has to be parallel. This is a very important condition here, is that the force must be parallel. It could be anti-parallel as well, you know, opposite direction, that's okay. But it has to be parallel to it. If it's perpendicular, you cannot, there is no work done there. You see what I'm saying? So in this case, the work here is going to be equal to, again, force times distance, but this time it's the force cosine theta. Write it better. Cosine theta multiplied by the distance x. Okay, this is very important. All right. I'll give you an example and show you what that means. A couple of examples. These are examples from my notes. I'm just going to call it example 1. So I think I did it already. Let me just do it again. Okay, so we have here a box. Here is the floor, and there is a force on it of 100 Newton. The box goes, so I pull or push, whatever you want to call it, the box some distance all the way to here. And let's say that this is the x equals 0 meter. This one is x equals 10 meters, okay? So the box went this way. As you can see here, the distance or the displacement is parallel with the force, so therefore this force is doing work. You got that? So in this case, if I'm going to calculate the work in this case is going to be F times delta X. So that will be F, which is 100 times 10 minus 0, and that will give me 1000 joule. Got it? Simple. Now example number 2. I have the same situation, except that now I am pulling the box or pushing the box with an angle. Let's say the angle here is the force that I'm pushing it with, and the force is also same data as we have above, and now this angle is 30 degrees, okay? And then the box goes from here to there, a total distance of 10 meters here. Same thing, starting from x equals 0. All right. So in this case, as I said, that you only take the force that is parallel with the displacement. Now the displacement is in the horizontal axis or the x-axis. So I'm just going to take the force that is in the horizontal direction, which is the x component of the force. So in this case, the work is equal to F cosine theta times delta x. You see that? So that's going to be 100 times cosine 30 times 10, right? I can do that in my head, I think. 100, because I know that cosine 30 is 0.866 times 10. And that will give me 866 joule. In other words, you're going to get less work done if you are pulling the box with an angle. You see that? I mean, in the beginning here, you're getting 1,000 because all the force is actually parallel with the displacement. Here, only a fraction of the force, only what, 86.6% of that force. So you're getting 866 joule. Got it, everybody? Okay. All right. I want to move on to the next topic. What I'm going to do, there's a lot of topics to cover in this chapter, so I'm going to go through them quickly, and then we'll start doing problems. I have several problems to do, at least 2 from the homework, and several examples, either from my notes or from the book. All right, the second concept that we need to cover is the concept of the kinetic energy. The word kinetic here, I am sure you know that, kinetic, it means motion, okay? So when we say kinetic energy, we mean motion energy, okay? In other words, if there is an object that is moving, regardless whether it is accelerating or not, if it's speeding up or slowing down, it doesn't really matter, or moving at constant speed, as long as it's moving, okay, as long as it has a velocity, okay, it has kinetic energy, period. Got it? And this kinetic energy, we have a symbol for it, capital K, okay, is equal to 1/2 mv squared. Here, m is the mass of the object, and this is and v is the velocity of the object, you know, the speed, whatever it is, okay? So, for example, let's say I am, let's say my mass, I think I am around 90 kilogram, roughly around there. And let's say I am walking, okay? So I'm walking down the sidewalk. And let's say with a speed of, let's say 3 meters per second. That's a little too fast. Let's make it 2. 2 meters per second, okay? So I have motion energy, kinetic energy. What is it? I can just calculate. So we have kinetic is 1/2 mv squared. So that's equal to 1/2 times my mass, 90 kilogram, times my speed, which is 2 squared. So that's going to be 4 to 180, 180 joules. So my motion energy, or the energy that I'm actually expending, okay, exerting, is 180 joule of energy. You get that? Simple. Okay. Now, the question is how work is related to the kinetic energy. There is an important formula, that's a question mark here. There is an important idea or theorem in physics. It's called the work-energy theorem, okay? The work-energy theorem. This is a very important formula. You need to understand it because you're going to see it again in Physics 152. When you take the second course in physics, you start studying electricity and magnetism. And this theorem is going to come back there, and you need to learn about it. So, you know, learn it once and for all. The work-energy theorem. What that means is the following. And there are, I mean, 2 energies here. We only covered the kinetic energy. Later on in the video lecture, we will cover the potential energy. But there is a relationship between work and energy, work and kinetic energy, and work and potential energy. So let's talk about work and kinetic energy. I'm going to explain it through an example, okay? Let's suppose that I am riding my bicycle. So this is an example. Let's say I'm riding the bicycle, okay? And let's say I'm going, while riding the bicycle, let's say my speed, let's call it V naught. Let's say my speed is, let's say 4 meters per second, okay? Now, also, let's assume that my mass with the bike, the total mass of both of us, let's say, for example, 150. That's too much. Let's say 120 kilometers. Okay, kilograms. Excuse me. Okay, so the total mass of me and the bicycle is 120 kilogram, and I am going at a speed of 4 meters per second on the bike. I'm cruising on the bike. Okay, now I wish to increase my speed. Okay, so what I do is I start pushing harder on the pedal, right? And I would push harder on the pedal, and until finally my speed is, let's suppose, my new speed, that is, let's say it is 6 meters per second. Okay, I still have the same mass, of course, right? Okay, so here's what the work energy theorem says. The difference between the two kinetic energies, the first kinetic energy when I was going 4 meters per second, and the second kinetic energy when I was going 6 meters per second, the difference between those two kinetic energies is exactly equal to the work. Isn't that interesting? So basically work says is equal to delta K, where K is the kinetic energy, so K final minus K initial. You got that? Let's calculate that with those numbers that we have. You remember K is equal to what? 1/2 mv squared. Please memorize it. So in this case, the work is equal to 1/2 mv squared. Shall we call it final here? Final squared minus 1/2 mv naught squared. I can take 1/2 m as a common factor just to make things easier. So v final squared minus v initial naught squared. There we go. And I can just plug in the numbers. So I have here 1/2 times 120, the total mass of me and the bicycle. V final 36 minus 16. And so let's calculate that. So I have times 60. Answer 1,200 joule. There we go. So the work that I have done is equal to 1,200 joule. Okay. Now remember, I could have also used work equals force times distance. That would be fine. Okay. But this is just another way of doing it. So now I have two ways of calculating work. I can calculate work as F equals, W equals Fx, provided that F here is parallel to the displacement. This is important. Or if I am given the kinetic energy, or I know some information about the nature of the motion of the object, then the work in this case is equal to 1/2 mv squared, the delta, that is, final minus 1/2 mv naught squared, or if you will, the delta K, okay? The difference in kinetic energy. Got it? Okay. All right. I want to do the potential energy first. I have a bunch. I'm looking at my my notes here. There's a lot of examples that I would like to do, but maybe I should hold on to them and then explain the potential energy. Then we'll start doing examples. All right. The second kind of energy, or shall we say the third, because we said work is energy, so that's the first kind. Then we have kinetic energy, and then we have now potential energy. Now, when we say the word potential, okay, if the word bothers you, you can replace it with the word stored. So potential, it means stored, okay? Let me explain it to you. Let's say I'm holding a stone in my hand, okay? Now, what will happen if I release the stone off my hand? I'm not going to throw it, I just release it. Well, it's going to drop down to the floor, correct? All right. Of course, in terms of forces, you can just say, well, it's gravity, it pulled it down, right? You get the gravitational force, and it goes into free fall. That's a correct answer. There is no problem with it. But if you want to explain it in terms of energy, here is how it works. We said that I am holding the stone in my hand. Well, let's assume that it was initially on the floor. So I picked up the stone and I started lifting it until I reached a certain height. Okay? So as I was lifting it, what's happening is that the stone started storing potential energy, storing energy inside of it. Okay? So when the stone is at a certain height, it has a certain amount of energy. The moment I release my hand off of it, the stone will start losing that energy, converting it into kinetic energy until it falls to the ground. Isn't that interesting? This is how we see it in terms of energy. Let me give you a diagram. So here is the height, okay? Here is the stone, okay? And because there is a height h here, I'll call it capital H for now, okay? It has a potential energy. I'm going to call it now, for now, PE, potential energy, or stored. And the moment I release my fingers off of it, the stone will begin to fall. And as it is falling, it's losing potential energy, but it is gaining kinetic energy. You see that? And that's why it speeds up. And by the time, right before it hit the ground, it's going much faster than, say, when it was here or here. Instead of saying it's faster. Why? Because it has gained the maximum kinetic energy at the bottom, right before it hit the ground. Okay? That's how we see it. Now, this potential energy, it has the symbol U, capital U, and it is equal to mgh. M here is the mass of the object. Let's say the mass of the stone here. G here is 9.8, and then you have the height. Got it? So, for example, if I say, as an example, let's say I have a stone in my hand. Stone has a mass, pick a mass, how about half a kilogram? Okay, half a kilogram. At a height of, let's say, 2 meters. Okay, so you look at this picture right here. Here is a stone at the height, capital H, of 2 meters, and the mass of the stone is half a kilogram. It's about a pound, half a kilogram. Okay, now I let go of the stone. So, but, well, let's forget about let go. Okay, the question here is, what is the potential energy here of the stone? Simple. All you need to do, you just apply the formula. U equals mgh, right? U here for the potential energy. The mass of the stone is half times g, 9.8, times the height is equal to 2 meters, right? And that will be 2 times half is 1 times 9.8. So the answer would be 9.8 joule. So that's 9.8 joule of energy. Instead of saying? Okay? Good. Okay, let me go back to the work energy theorem, because I want to explain it in light of the potential energy. Work energy theorem. So far we said that the work has there are 2 ways to calculate work. One is the work is equal to Fx or Fs, where the force here is parallel to the displacement. And also we said that the difference in kinetic energy will also give me the amount of work done. You see what I'm saying? Done by the system. Okay. Now there is a third way. Here is, again, I want to explain it to you through an example. Let's say, let's say I have a table here. This is a table. And let's say there is on the table there is let's say we have a book standing on the table right here. Here is the book. All right, there we go. And what I want to do, I want to hold the table and put it on top of this shelf right here. Okay, so assume that the table is, or the book rather, is at some height, let's say 1 meter from the floor. The floor is right here. Okay, and the shelf is, let's say, 3 meters. That'd be too high, wouldn't it? Let's say 2. From the floor, the same floor. The floor is right here. So, okay. So what I do, I grab the book and I lift it up with my arm, with the muscles of my arm, if you will. And I lift it up and I follow, let's say, this path. And then I place the book right on the shelf. And that's it. What I have done here, I have done work because I have expended some energy. Make sense? Okay. So what you do, if I want to calculate that amount of work, like I said, you can use one of those, but here the motion doesn't really apply to it. You know what I mean? What applies to it is the position of the book here and the position of the book here. Just like what we said about the potential energy here, is kind of a function of position. Notice that it is mass g. These are both constant for the object, but the one that changes is the position, the height from which it was, where it is situated, whatever. Okay, so what's happening here is that initially, right here, before I lifted the book, it has a potential energy. Let me call it U naught equals to mg h naught. The naught here initial, which is equal to 1 meter. Here, the final potential, if you will, is equal to mgh, let's say final. Okay, where the final height here is 2 meters. Okay, the work energy theorem states that the work is also equal to delta U, the difference in the potential, U final minus U initial. So that will be mgh final minus mgh initial. I can take mg as a common factor, and I have h final minus h initial, and I can just plug it in. The mass of the book, whatever it is. Let's put some data. Let's say the mass of the book is 0.5 kilogram. G, of course, 9.8. So now let's plug it in. So we have here 0.5 times 9.8 times the final height is 2 minus the initial height is 1, and that will give me 4.9 joules of energy. In other words, what I have done, I have expended 4.9 joules of energy to lift the book from the table to the shelf. You get that? So that's another way to calculate work. So now we have 3 of them. I'm going to write them down once and for all. Here it is. So work is equal to Fx equal to delta kinetic energy. Let's call it delta Ke. It's also the delta potential energy, delta Pe. Okay? Keep those formulas in mind. You will see some problems here and there where you need to use them. Okay, good. I want to start with, now I want to begin doing problems. There is one more concept, which is the concept of total energy. I'll talk about it later. Let me do a couple of problems first. So I'm going to start with example 7.3. That's a nice example. It's not the simplest example, but it's a very nice example. Let me look at the hard copy and just find it. 7.3, page 187. Right here. There we go. So you have a tractor. Let me just show you so you have a tractor, and then you have a sled, and then there is what is that, firewood on it, and the tractor, the farmer is using the tractor to pull this whole mass, okay, at a certain distance. Okay, so he says here a tractor is hitched to a sled loaded with firewood and pulls the sled a distance of 20 meters. Okay. Again, when you read a problem, always write down what's given. Okay, this is important. So as you read, you're writing it down. Okay, I wish I could use my my OneNote while reading the book. I have to kind of switch between them. I can't do it. But anyway, so we have the distance here at 20 meters along a level frozen ground. Okay, the total weight of the sled and the load is 14,700 Newton. Pay attention to the unit. It's not the mass, it's the weight, mg. Okay. The tractor exerts a constant force, we'll kind of call it T, capital T tension, with a magnitude of 5,000 Newton at an angle of 36.9. See the angle right there? Okay. A constant 3,500 Newton friction force, which means going this way, opposes the motion. Find the work done on the sled by each force individually and the total work done on the sled by all the forces. Okay, that's a nice problem. It's a mouthful. All right, let's see how we do this problem. Example 7.3. Okay, so what you have, let's draw the tractor. I think I can draw a tractor. A small wheel and a big one. That kind of, all right, and then I have the sled. Let's just turn it into, here is the floor, the ground, and here is the sled. Let's just turn it into, you know what, I'll make it a little closer. So it's being pulled like that with a force, I'm going to call it tension, T, okay? And the angle here, I'm going to call it theta for now, but it's given to us, okay? And then, of course, the tractor is moving in this direction. Okay. I think, let me look at, as I look at, I don't want to keep switching. Let me just write down the data. I have it right here in my book here. He said the tension is equal to 5,000 Newton. And he said the weight of the sled mg, I like to call it mg, is 14,700, excuse me. The angle, theta, is 36.9 degrees, and you have a friction force of 3,500 Newton. Okay, these are all the data that was, oh yes, and the distance traveled, or the sled was pulled a distance of 20 meters. Is that right? Yes, 20 meters down the road, if you will. Okay, there we go. Okay, now he's saying that find the work done by all forces. I'll explain all of that in a second. Just bear with me. I want to write it down first. Okay, there we go. So we have that. What does that mean? Well, first thing, I want to put all the forces on, okay? So what I have in here is, I'm just going to concentrate on the sled. Here is the sled. The tractor is not really important. It's what's important is the force the tractor is producing. So here is the sled. You have the the mg of the sled given to us. Of course, we have the normal. You always put the normal whenever there is a friction. Here is the friction force. And then we get that tension, which is like that. Here is the tension. Here's the angle, theta. There we go. Anything else? I think this is it. These are all the forces on, that's basically the free body diagram. Okay? All right. What he's asking for, see, every force here, how many forces do we have? Tension, normal, weight, and friction. So we have a total of 4 forces here. Every one of them is producing work. He said, what is the work done by every force? Okay? Keeping in mind what? That the force must be parallel with the displacement. Remember, the displacement is in this direction. Okay, and it's equal to 20 meters. You see what I'm saying? So now let's start with the force, the work done by the tension T. Okay, keep in mind, work is equal to Fs, or Fx. Shall we call it x? I'll call it x. I don't want to confuse you. There we go. Fx. That's the master equation that we have, right? This is the one we're going to be working with. Now let's start with the work done by the tension. So I'm going to call it work subtension. So that will be tension times x. But hold on a minute. Look at that. The tension here is not in parallel with the displacement. So only the component that is parallel with the displacement is producing the work. The perpendicular one, the one along the y-axis, is not producing work. You see what I'm saying? So you want to be very careful. So what I've written here is not terribly accurate. So it is t cosine theta times x. Now I can calculate that. Well, he said the tension, right here, tension is 5,000 given to us. Theta is 36.9, and the distance x is 20. So we have everything. So the work done here is going to be 5,000 times cosine 36.9 times 20. When I calculate that, I get 80,000 joule. There we go. This is the work done by the tension. I'm going to box it because I'm going to come back to it in a sec. Now, is this work positive or negative? Here is how you can tell. Go back to this picture and then run your film. I mean, here is the tractor. I hope you are running the film in your head. You see how the tractor is going. The tractor is going in this direction, and the sled is following it also in this direction. You agree with me on that? And the force, well, look at the force, the x component of the force, this one. This force, F cosine. Well, it's in this direction as well. So it's in the direction of the motion. It's also in the direction of the displacement. The displacement is this way, correct? Now, if the force that I'm calculating for the work and the displacement are in the same direction, the parallel and the same direction, not anti-parallel, then the work is positive. Okay? You may say, well, what does that mean? Okay, hold on. Let's calculate the work done by the friction. Look at the friction. Look at the vector of the friction. It's this way. And the displacement this way. Are they parallel? Yes, they are. Anti-parallel. Opposite in direction, but they are still parallel. You get that? This is parallel. We can call them anti-parallel, but they are parallel. You got it? So you can have it this way. These are parallel, positive. The work would be positive. If they are in this situation like that, the work would be negative. This work is positive. Okay? That's one way to do it. So here we have the friction is in the negative, or in the opposite direction of the displacement. So in this case, the work that is done by the friction is going to be equal to, we can just say minus F times X, and that will be equal to, what is the friction? Yeah, he gives it to us right here. Friction, he said 3,500, so that's going to be negative 3,500 times 20, correct? And that will be equal to negative 70,000, I don't like commas, 70,000 joule. There we go. Okay? All right, one more. Let me box it. What about the work done by the weight? By the weight of the sled right here. Okay? Well, look at it. The weight is perpendicular to the displacement, correct? 0. Make sense? What about the work done by the normal force? 0, for the same reason. The displacement is this way, and the normal is this way. Normal to the surface, perpendicular surface, so 0. Now, let me go back to the problem and just read the question again. He says, find the work done on the sled by each force individually. This is what we have done now. And the total work done on the sled by all the forces. Okay? All right. So there we go. We have, these are the 4 forces that we were dealing with. So the work total is equal to the work done by the tension plus the work done by the friction plus the work done by the weight plus the work done by the normal. Add them up. Work done by the tension is 80,000, and it's positive. I need to remind myself of that. Work done by the friction is negative because it's in the opposite direction, and that's 70,000. Plus work done by the weight is 0, plus work done by the normal is 0, and there we go. So I have plus 80 minus 70, and that will give me the total work is 10,000 joule. That's the total work done by the system, the whole system. You got that? There we go. Now, there is a continuation to this problem, and that is in example 7.4. So I'm done with 7.3, but we're not done with this problem because it continues on example 7.4. So let's go to it. In between, he explained the work energy theorem for kinetic energy, which we already talked about it. So it's on page 190. All right, he says here, let's revisit 7.3, the one we just did. Okay, he says, we found that the total work, okay, so he said we found that the total work done on the sled by all the forces at 10,000 joule. There we go. This is what we got right here, right? Okay. So the kinetic energy of the sled must increase by 10 kilojoule, he's saying. If you don't know why, it's okay. I'll explain it in a second. Let me just continue reading. Remember, he said, so the kinetic energy of the sled must increase by 10,000 joule. Okay. The mass of the sled is equal, okay, suppose the sled's initial velocity is that. What is the final speed? Okay, so he's babbling here. Okay, basically what he's saying, if the initial velocity of the sled is 2 meters per second, what is the final speed? We want to calculate all of that with the work energy theorem. So here, example, given that the initial velocity is 2 meters per second, what is the final speed after 20 meters? You see what I'm saying? Let me just revisit this. Remember we said, here's the tractor pulling the sled, started at x equals 0 right here. Okay, and then he pulled it all the way for 20 meters, all the way to here, right? Started with a velocity, he's saying, of 2 meters per second. This is in example 7.4. What is the velocity here? That's what he's saying. After it traveled 20 meters. Got it? Okay. So, how do we do it? Well, let's go back. Again, let's assume that you are required to use the work energy theorem. Now, remember, there are two versions for the work energy theorem. W equal delta K, Ke, and W equal delta Pe, potential energy. Now, potential doesn't apply to us because potential has to do with gain and height, up and down thing. Okay, there is no gain in height here, so basically we can ignore that. However, he mentioned speed and all, so I know that this is going to be it. Okay, so what is delta Ke? The value. Well, the value, according to the work energy theorem, must be equal to the work. See that? The work is equal to delta Ke. Ke is what? Delta Ke is basically K final minus K initial. You see what I'm saying? And that's equal to the work. Well, what's the work is equal to? We just calculated from the previous example. It's 10,000 joule. Make sense? So this is 10,000 joule. Okay? So let me write it down in a clean way. So I have here 10,000 joule equals Kf minus K naught or Ki. All right? Now what is Kf? 1/2 m V final squared minus 1/2 m V initial squared. Take 1/2 m as a common factor. V final squared minus V initial squared. So far so good? Okay. Well, he said that the V initial is V naught. I'm sorry, I keep switching different notation. This is VI, right? So V initial here is 2. So I already know what it is. And I just need, remember, he's asking for the V final here. This one right here. This one right there. And that's going to be final. Okay? And now I need to calculate V final. And, well, I need to know what M is. Well, he said that the weight from the previous example, here, let me show it to you quickly. He said, let me find it. Here we go. He said the sled weight is 14,700 Newton. Right? So in this case, the mass, he said that mg is 14,700 Newton. Therefore, the mass is 14,700 divided by 9.8. That'll be equal to, let me look it up very quickly, 14,700 divided by 9.8, 1,500 kilogram. That's about 1.5 tons. There we go. This is the mass of the sled. So now I can plug in all of that into this formula to solve for V final. Again, I would like to do the algebra before I do that. So let me take m over 2 here. So that's going to be 20,000 divided by the mass plus VI squared equals VF. I did a couple of steps in my head. You can do it. You can do it yourself and see if you arrive at the same formula that I have. So that's going to be 20,000 over the mass plus VI squared to the under the root. That's the final expression. Now plug it in. So I have 20,000 divided by the mass, 1,500, plus VI. He said it's 2 squared, which makes it 4, under the root. Let's calculate that. So I have here 20,000 divided by 1,500 plus 4 under the root. I hope I did it right. I got 4.16. Let me write it down. I'm not sure. I need to look up the book. I got what? 4.16 meters per second. Let me look up the book. Yeah, 4.16. He got the same answer. There we go here. Right there. Oh, you go to the next page. Again, you can do it your way. There we go. 4.16 right here. So anyway, and there we go. We have the final velocity. Okay? There is a continuation to this problem, if I remember correctly. Here, he said the reflection here. So we got he said this problem can also be done using work energy theorem. We can find the acceleration and then use the equation of motion for constant acceleration. You know what? I'm gonna ignore this part. This is good enough. This is not what. So I'm gonna stop here. Okay. All right. Let's move on. Oh, okay. So there is now a bunch of small topics I want to talk about. Unfortunately, this chapter has a lot of topics, and each of them is like a half a page. So I need to cover all of them before we start doing problems. So we're going to come back. If you remember, back in chapter 6, we talked briefly about the spring constant. Remember that? So he talks about that here as well. So let me just go back to what I've said about the potential energy. Remember, the word potential means what? Stored. And it can be different kind of stored energy. It could be gravitational. just like what we have been dealing with, mgh, that's gravitational, because there is g here, you know, the acceleration to the gravity. So that's gravity, and it depends on the height. It's a function of the height. There is also spring potential energy. Okay? What that means is the following. Let's say here is a wall, this is the floor, and let's say I have a slinky, okay? And I have the slinky, one end of it is attached to the wall, and here is the slinky. It's unstretched, just sitting there on the floor, not doing anything, okay? Now what I'm going to do, I'm going to take the slinky, here's the same slinky, and I'm going to stretch it. So now it is stretched. Let's say stretch it all the way here until here. Okay? So remember, it was right here. How much stretch there is here? 0. It just relaxed. And when it's relaxed, the length of the spring is not important. What's important is the displacement, or the stretch, or the compression. As long as the spring is relaxed, the length of it is not important. It could be really small, it could be really big, it doesn't matter. What matters is the stretch. Because the moment you start stretching it or compressing it, you are adding stored energy, spring energy. You got that? That's the concept behind it. So here there is really no energy whatsoever when x is equal to 0. Remember, x here is the displacement, or what's x here? It could be either stretch, how do you spell that thing? Stretch, or compression. Okay, either or. And the general term for this x is the displacement of the spring. Displacement. Okay? Alright, so in this case right here, it has 0 displacement because the spring is not stretched or compressed. Now I pull it. Okay, so I pull it from here, x equals 0, which is right here, all the way to here. Let's say x equals, say, 1 meter. All right, let's say 1 meter. Okay, so what happened now, there is new, or energy in here, stored energy U, and this energy U is equal to 1/2 kx squared. Very important formula to keep in mind. Okay, the k here, of course, is the stiffness constant, or the spring constant. Stiffness constant. It just basically tells you how stiff the spring is. The slinky is not very stiff, as you know, and so therefore this number would be small compared to a spring that is much stronger than that. Again, your book would be called spring constant or Hooke's constant. Okay. So one more thing. What caused the spring to be unstretched to stretch? What did I do? Well, I exerted a force on it, didn't I? That force that I exerted is equal to kx, x being the displacement from here to here. See what I'm saying? So that's F equals K. I'm going to write it down again somewhere else. I don't want to clutter the whole area here. So I exerted a force, F equals Kx, to pull the spring from position x equals 0 to x equals 1 meter. Okay? So those are the two formulas. It's this one and this one. For our subjects this chapter, we're dealing with potential energy. So this is the potential energy of the spring, 1/2 kx squared. Okay? For those of you who have taken calculus, the potential energy is always the integral of the force, dx. Okay, if you haven't taken calculus, you can ignore that. So that's integration of kx dx. Well, k here is a constant, so I can take it out of the integral. So I get x dx. Well, what's the integration of x? X squared over 2, which is that. Okay, that's in advanced mechanics. Basically, the potential is the integration of a force. But anyway, all right. We also talked about the gravitation. Okay, the last two more topics, and then we'll start doing problems. and that is the conservation of energy. Now, this is probably the most difficult concept that students have difficulty understanding. So I'm going to just tell you what it is, and then I'm going to explain it to you through solving problems later on in this video. So, the conservation of energy. Okay, we define something called the total energy. Capital E, okay? That's the total energy. And this total energy is defined as the sum of the kinetic plus the potential. You need to box this equation and memorize it, because you'll be solving problem using this one. Okay, so the total energy is equal to the kinetic plus the potential. And this total energy, sometimes we refer to as the total mechanical energy. So just to distinguish it from thermodynamic energy, for example, mechanical energy. Okay, and of course it's the sum of the kinetic plus the potential. All right, let me give you a very simple example of what that means. And I'm sorry. When we say conservation, it means this sum K plus U is always the same number, no matter what. Okay. In other words, this E is always the same. That sameness, or that constancy of that value, is what we refer to it as conservation. Let me give you one simple example. Imagine I have, let's say you have, this is you here and that's me, okay? Let's say in terms of money, okay? There's money. This is how I explain it to somebody who've never heard of conservation of energy. It's kind of a silly example, but I hope it will help you visualize it. Okay, so this is me and you. Let's assume that you don't have any money, all right? Zero money. Okay, your money is zero. You have no money whatsoever. I, on the other hand, I have $20. Okay, so I have $20. You don't have any money at all. Okay, so this is all the money between us. So what is the sum total of the money between you and me? Well, it is 0 plus 20 is equal to what? 20. Okay, now what I do, I give you $1. So what's left for me? 19, right? Now you have more money. You started with no money. Now you have $1. I get less money, but what's the sum between us? 20. Okay. Now let's say I give you $5. Okay, so I give you 5 more. So now your money is $6, right? So I added $5. Yeah, remember you already have $1. I gave you another 5. Now you have $6 total money. And now what I have is 13, right? Now if I add up the total money between us, it's 20. Let's say I give you another $10. Okay, so now you have 16, and I have what? 4. The sum of the money is 20, and so on. Are you getting what I'm saying here? What I'm saying is this. We can exchange money between us all day. The sum of the money that you have in your pocket and the sum of the money that I have in pocket will always be $20. See that? That's conservation. That's the essence of the word conservation. You can shuffle money between you and me all day, down to the pennies. Doesn't matter. But the sum will always be, say, $20. Okay? Look at this this equation. When we say conservation of energy, it means kinetic plus potential. Think of it like I am kinetic, you are potential. I have $20, you have nothing. Okay? But the sum between us will be 20. Then I lose a little bit of kinetic energy. Now you gained a little bit. Now you have 1 joule of energy, and I got 19 joule of energy. It will be 20. Now you have 6 joules of energy. That means I have, did I copy this wrong? Should have been 14 here, right? There we go. Sorry. So I have 14 joule of energy. You have 6, and the total is 20, and so on. You get that? That's basically how it works. So the sum of kinetic plus potential will always be the same for that total energy. Okay? That's the meaning, the essence of the word conservation. All right. I want to use this concept, okay, to solve a problem that we have done before. Here it is. let's say I have a height, I have a stone, okay? Let's say the stone, let's say, pick whatever number you want. Let's say it is 0.25 kilogram, all right? And it is, I'm holding it between my fingers at a height of, let's say, 1 meter. I let go of the stone. I want to know what is the speed of the stone just before it hit the ground. Speed of the stone just before it hit the ground, hit the floor or ground. Okay? Make sure you understand the problem before I do this one. It's a very simple problem. I know you've done it before, and it's easy. So if you want to do it, you're going to say, "Oh, well, I can use Freefall Kinematics," which is correct. So let's use Freefall Kinematics. Let's say I want to use the second one, this one. V squared equals V naught squared minus 2GY. Is that right? Remember, I want to know the speed just before, I want to know the speed here. The initial speed, remember, I'm holding it between my fingers, is 0, right? So when I use it, let me ignore the minus sign here because the y here is minus and that's minus become plus. So I'm not too concerned about the minuses now. Let's keep it like this. Okay, you agree with me that the initial speed is 0. So the velocity is nothing but the square root of 2gy. There we go. That's easy. Y is given to me right here, 1 meter. I just plug it in, 2 times 9.8 times 1 into the square root. I get the velocity. You don't need to get it, but there we go. This is how you do it, right? Freefall kinematics. You agree with me on that? Good. Now, I want to find this velocity using conservation of energy. Pay attention now. I want to show you that I'm going to get exactly the same equation. That's what I'm trying to say. Here is how it works. Let me redraw this picture again. Here it is. Here is the stone. Here is the height. Call it H, whatever you want to call it. Let's call it H. Okay. What you want to do, of course, I want to find the speed of the stone just before it hit the ground, right here, right? So I call this position 2. Well, there's no need to call it anything. If I ask you the question, remember, I am here, I am holding the stone between my fingers, or in my hand, right? And I ask you at the height h, 1 meter, and I ask you, what is the total energy of the stone? Well, the total energy of the stone here, before I throw it, is kinetic plus potential. Well, what is the kinetic equal to? Remember, kinetic is what? Motion energy. Is there any motion to the stone? I'm holding it. So that's 0. Plus potential. Is there a potential? Yes. As long as there is height, there is potential. Okay? Remember that. If there is height, there is potential. If there is motion, there is kinetic. If there is height and motion, then you get both of them. Got it? It's easy to know if there is potential or not. Is there a height? If there is potential. Is there a compression of the spring or a stretch of the spring? There is potential. Okay. So here we have, is there a height? Yes, there is, right there. There is a height, obviously. So there is potential. It's equal to what? mgh. Remember that? Potential is equal to mgh. Okay, there we go. So energy is equal to, the total energy here is equal to mgh. The kinetic is 0. There we go. Now let's come right here. Right before it hit the ground. What's the height right before it hit the ground? Well, it is kind of an infinitesimal height. It's extremely tiny. So tiny that you can just say it's really practically 0. You see what I'm saying? So we basically could ignore that height because it is so tiny. So now when I have the total energy, which is K plus U, the height here, or excuse me, the potential, which is dependent on height, the height is so tiny, I can just say that the potential is 0. And I'm left with what? 1/2 mv squared. Okay, I mean, basically what happened, you had stored energy here, potential, and you let go. As it's losing height, it is gaining energy. Excuse me, kinetic energy. Okay, so as it is gaining the kinetic energy, and here is this maximum, so it becomes that those two must be equal. Anyway, so there we go, plus 0. And so in this case, the total energy here is 1/2 mv squared. Okay? Now here is the $20 question. How this E is related to this E? Conservation of energy. Total energy is a constant, just like the $20 example here. That's why I call it the $20 problem. So that means this amount, mgh, must be equal to this amount, 1/2 mv squared, because energy is constant, energy is conserved. Now equate them together. Must, oops, mgh equals 1/2 mv squared. See that? This one is equal to this one by the conservation law. Look at the masses, they cancel out, right? So I have here GH equals, or G capital H rather, is equal to 1/2 V squared. Solve for V, so may move the 2 here to the other side. The V becomes square root of 2GH. And guess what? Look at this equation. And look at this equation from kinematics. Exactly the same equation. 2gy. Here is square root of 2gy. This one is square root of 2gs. Exactly the same equation. See that? So we can either use freefall kinematics to get that velocity, or we can use the total energy. Okay? The subject of this chapter, you're going to be using the total energy. Okay? Okay, good. Of course, it's more complicated than that, and we will be doing some problems. I'm going to start with, okay, one more topic. Let me just go over it very quickly. This is probably the simplest topic, actually. Let me just go over it, and then we'll start doing problems. And the last topic in this chapter is the concept of power. Okay? The formal definition of power is this: the work done during a time interval delta t. Okay? That's basically the definition of it. What that means is the following. The symbol of power is capital P is equal to work divided by the time. Okay? In general, actually, it's work is energy, any kind of energy, divided by time. You will learn this later when you study electricity and magnetism and thermodynamics. You're going to come to that concept of power, and it's basically, this is the definition that you will be dealing with rather than work. But for our case here, for this chapter, we're going to say it is work per time. Remember, work is energy, so it's energy per time. What that means is the following. Let's say, for example, well, the unit of power, think about it. If it's work per time, that makes it joule per second. Is that right? And this joule per second, we call it the watt. And it is the capital W for the unit, the symbol of the unit. Okay? Well, I'm sure you are familiar with the concept of watt because I'm sure you bought a light bulb from the store before. And when you buy a light bulb, here is a light bulb. Right? And then when you, let's say that you buy a light bulb of 75 watt. Not terribly bright, but you buy something like, say, 75 watt. What does that mean? When you buy a light bulb of 75, it means that this light bulb is giving off energy, light energy that is, of 75 watt. 75 watt means 75, go back to this, joules of energy per second. That's the meaning of it. That's how much energy it is expending, or it's given off. It's given off 75 joules every second of light energy. Okay? That's the meaning of it. So power, work per time, the best way to think about it, just energy per time. How much energy is given off? How many joules per second? Okay? All right. Let's go back to the definition again. So power is work per time. Well, we know that work is equal to F times X, or S over time. And we know that X over T is what? That's velocity, speed. So we can say that it's also equal to the force times the velocity. So that's another form of power. So the force times the velocity. It's going to come in handy sometimes. So now we have two formulas to deal with. Power is equal to work over time, energy over time over here, or force times velocity, depending on what's given in the problem. For you, you're asked to calculate the power. Here is an example. Example 715. Very quickly, we'll do that. It has to do with power. Let me try and find it. Let me find it in the hard copy first. Lots of pages to flip. Did I say 715? Yeah. Oh, it's the very last page of the chapter. Okay. Page 208. I pretty much covered the entire chapter, nothing skipped here. Here is the power right here, the average power. So work is F delta S over time, so it becomes the force times the velocity. Okay. So let's look at this example here. Example 15 right here. It says a jet airplane engine develops a thrust, okay, a forward force on the plane of 15,000 Newton, roughly 3,000 pounds, when the plane is flying 300 meters per second, roughly 670 miles per hour. What horsepower does the engine develop? Okay, well, we'll talk about horsepower in a second. Basically, he's asking for the power. What is the power? If you are given the force, okay? So what that means is the following. So here is the plane. Let me just show you a picture of what it looks like. I mean, a picture of the problem. So here is a plane. I can draw a plane. There we go. And, of course, there's the jet engine, I think, on the wings here. So it's pushing like that. That force, the thrust, is equal to 150,000 or 15,000? Sorry, 15,000 right here. So we have 15,000 of thrust, and then the plane is going with velocity of 300 meters per second. And he wants to know the power. Well, the power is what? Force times velocity, right here. Where is it? Right there, right? So we can just plug it in. So that's 15,000. Multiply this by the velocity, the speed, 300. And when we calculate that, I get 4.5 times 10 to the power of 6 watt. Basically 4.5 million watts. What that means is what? The plane engine is given off 4.5 million joules of energy per second. Okay, that's the meaning of it. Now he said how many horsepowers, HP. Well, a horsepower is just a unit, okay? So just a unit conversion. We know that 1 horsepower is equal to 746 watts. Doesn't matter how we come up with it, but just got to remember it. So there we go. Simple. All you need is just to convert it. So let's do the conversion here. So we have the power is equal to 4.5 times 10 to the 6th watt over 1. Remember I showed you how to calculate, how to convert units? So this is on the top, I'm gonna put the watt here, horsepower here, 1 horsepower, 746 watt, and then you just calculate that, and it turned out to be 6030 horsepower. There we go, here's the power. Got it? This is a very, very large energy. Compare this to your car. A typical car would be what? You know, I have a minivan. I think the power on it, I think it's 120, I think. So that's really, really powerful. Okay, good. Now let's start doing problems. I think I'm done with the chapter, covering the chapter, and I have several problems to work on. And let's start with problem number 716. These are all homework problems. I would think they are. 716. Yes, this is a homework problem. That's on page 214. Right here. Shall I make it big? As big as possible? There we go. That's too big. There we go, right there. Okay. It says you throw a 20 Newton rock, that would be the weight, right? Divided by 9.8, you get the mass. You throw a 20 Newton rock into the air from the ground level and observe that when it is 15 meters high, it is traveling upward with 25 meters per second. Now that's interesting. What does he say here? What is he saying? Well, he gives you the mass of the rock, or the weight of the rock, and then he says when it is 15 meters high, what is that? That's the height of the stone at some instant of time. So if there is height, there is what? Potential energy. Remember, height, potential, speed, kinetic. So he said when the stone is 15 meters high and it is traveling 25 meters per second. So it has kinetic and it has potential. This is what I'm reading. As I read that, this is what comes to my mind as I go on. Okay. He says, use the work energy theorem. You know what? I'm going to use conservation of energy to find the rock speed as it left the ground. Okay, basically he wants the initial initial speed of the rock. Okay. And B, what is the maximum height of the rock will reach? Okay, this is basically a kinematic problem. We can use kinematic to solve it, but I'm going to use conservation of energy. I'm going to show you how to do that. All right, here's how we do it. Try to avoid using the work energy theorem and just work with the total, the concept of conservation of energy. This one, E equals K plus U. It's much easier and straightforward, in my opinion. All right, so we have problem numbers 7.16. He said the weight of the rock, which is the mg of the rock, is 20 newtons. It's a rock. And what you do, here is U, all right? Here's U. Here's the ground. You throw the rock, let's assume you throw the rock from the ground, okay, somehow, and it goes up, 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 until it reaches a maximum height, and it comes down. It's a parabolic path, not like my path here, okay? So this is a parabolic path. Let me draw it better. The rock reaches the maximum height. However, he says, when the rock, look at that, he says, when it is 15 meters high, it's traveling upward 25 meters per second. So let's draw that. So here is 15 meters high. Let's say here. Okay, so this is the height, 15 meters. It's traveling upward, he said upward, of velocity of, what is it? 25 meters per second. Got it? He gave you this information. Now he's asking for what's the speed, the initial speed of the rock, right here. I'm going to call it V naught. So he wants V naught, what is it? That's part A. And B, what is the maximum height reached by the rock, which basically this one. Did I say maximum speed? Maximum height, okay? Let's call it big H. Call it whatever you like. I like it, call it big H. There we go. Now, again, you can pause the video and solve this problem with Freefall Kinematic. No problem. You will get the right answer, okay? But how do we do it using the conservation of energy? Here is how it works. Remember, E here is a constant, correct? Okay. Before I do anything, let me just get the mass of the rock. Just get things going. So here I'm given the weight of the rock. Let me get the mass. So the mass here would be 20 over g. So the mass would be 20 over 9.8. So the mass of the rock, in this case, I use my calculator, 2.04 kilogram. There we go. Okay, what I want to do now, he gives me this information here, the state of the rock here. At this position right here, it is 15 meters high, and it is and it's going at the speed of 25. Okay. By the way, what's cool about energy method, you don't bother with signs, whether it's vector up or down or left and right. You don't bother with it. You just put the numbers in positive and that's it. You don't need to worry about that, because energy by its own nature is a scalar quantity and direction is not important. So you don't bother with that. Okay. So let me get the total energy. The total energy of the rock in this position right here, okay, it's K plus U. That makes it 1/2 mv squared plus mgh. What is h? H is 15. So let me get that total energy. 1/2 times the mass of the rock, I just got it, 2.04, times the velocity, he gives it to me, 25 meter per second squared, plus the mass, 2.04, right? The mass times g, 9.8, times the height is 15. I want to calculate all of that. So you want to calculate this this part right here plus this part right here. And when I do that, I get the following. I get 637.5 plus 300 joules of energy, that is. So the total energy is 937.5 joules of energy. This is the amount of energy the rock has right in this location right here. Okay, guys? But by the conservation law, this amount of energy is also the amount of energy of the rock here at the lowest point, and here, and anywhere here, all those dotted lines, anywhere through the path of the rock. The constant energy, the energy is always going to be 937.5 joule. Got it? Now we come back to his question, part A. He says, what is the initial velocity? Right there. Got it? Well, let's do it. Again, I use my conservation of energy. E equals K plus U. U is what? Potential. Depends on height. What's the height of the rock here? 0. Correct? So this is 0 right here. With no height. So the whole thing is basically 1/2 mv naught squared. And what is the total energy? E right here. It's this one right there. So you're going to put it there. 937.5. And all I need to do now is to solve for V naught. So V naught is equal to 2 times 937.5 divided by the mass. And then you just, under the root, of course. And then you calculate that. So you have the square root. I'm trying to erase this stupid thing. Come on, erase. There we go. So we have 2 times 937.5 divided by the mass. I just got the mass. It's right here, 2.04. And then I would use my calculator to calculate that, and I got, when I do it, I got V naught to be equal to 30.6 0.32 meters per second. There we go. I have the initial velocity. See that? Again, you can use the kinematics and get the same answer. Now we come to part B. Part B says, the maximum height reached by the rock. Okay. Well, the maximum height is right, let's go look at the picture, right here. What's the value of the total energy here? Exactly the same. And what's going on here at the maximum height? What's the speed at the maximum height? Well, the rock stops before it starts descending down. So here at the top, we have potential, but we don't have what? Kinetic, because there is no speed here. The velocity here is 0, right? So we have here E equal kinetic plus potential, but there is no kinetic. Rock stopped. Okay, so therefore velocity 0. So here I have E equals mg capital H being what? The maximum height. And of course energy, E, is what? The same energy we use right here, because it's conserved. It's always the same number. The sum is always the same. So that's going to be 937.5. So 937.5 equal the mass 2.04 times 9.8 times big H, and therefore if I do the algebra and calculate H, I will get 46.9 meters. There we go. I got the height. Got it? This is a very, very good problem. If you understand it, then you understand the concept of conservation. All right, one more. I'll do 2 more, then I'll stop. Oh, 41 is hard. I'm going to do 41. Let's see. I'll do 19. 19 a little bit toughy. 19. Right here. Right there. Okay? It says a block of ice with mass 2 kilogram slides 0.75 meters down an inclined plane that slopes downward at an angle of 36.9 below the horizontal. All right? If the block of ice starts from rest, now this is important. Why? Because start from rest, that means the initial kinetic energy is 0. All we have is potential. What is the final speed? Okay, you can ignore friction. Okay, let me show you a picture of how it looks like. Again, always draw a picture. It really helps. Number 7.19. So what I have an inclined plane that looks something like that. Again, the good news, you don't need to deal with vectors, weight, and mg cosine and mg sine and all that. Okay, so you have a block of ice sitting right here. Okay, he says that the block of ice has a mass of 2 kilogram and is sliding down the inclined plane. Now let's read the problem carefully. Look at that. Look what he says here. He said slides 0.75 meter down the inclined plane. That means the sliding along this way. Okay? 0.75 meters. Until the end, something like that. Where this distance, shall we call it S? 0.75 meters. Okay? Just like that, okay? The angle here is theta. He gives it to us. 36.9. He said the block starts from rest. If the block starts from rest. So the initial velocity right here, guys, is V naught is 0. But we do have what? We have height, which means we don't have initial kinetic. You know, kinetic is 0, the initial, but we do have potential because we have height, this height, which we don't know. Okay, that's the tricky part about this problem. What's the final speed of the block? So basically he wants to know, what is the final speed of the block this way, this velocity, right down there. You see what I'm saying? All right. Again, we can use conservation of energy. I'm going to do the following. I'm going to do, what is the total energy here when the block at rest, when I let go of the block, and what the total energy here right before it hit the floor, if you will. Those two total energy must be equal by the conservation law. I'm going to equate them together and solve for V. You see the plan? So remember, the height of a block is always vertical height. That's not a height right this way. Got to be the vertical height. In other words, the height of the block basically is the height of this side of the triangle. Let's call it H. Okay? Well, how do we get it? Well, let me draw this triangle again. The triangle looks something like that. This is what I'm seeing. Whoops. The hypotenuse here, I'm trying to erase the hypotenuse. Get out of here. The hypotenuse has a length of 0.75, right? I want this one, and I have theta. Simple, huh? He gives me theta. So basically, the height in this case is going to be, that will be opposite. So let's say sine. Sine theta is equal to h over 0.75. So therefore, the height is 0.75 times sine 36.9. Is that right? Then I can calculate that, and that will give me, let me use my calculator. So I have here sine 36.9 times 0.75, answer 0.45. Okay, the height of the triangle, excuse me, the side of the triangle, or the height of the block initially, 0.45 meters. There we go. Okay, I got it here. Now I go back. So let me call this, just to clarify things for those of you who are having a problem, let me call this position 1, and this is position 2, okay? So let me find E1. Well, E1 is just K plus U. K here is the initial. But since he said the velocity initially is 0, so K naught is 0, right? So all I have is mgh. I have just calculated h right here. So I can find the total energy in position 1. The mass of the block is 2 times 9.8 times 0.45. And I can easily find that. And that will give me, let me do it again. 0.45 times 9.8 times 2, answer 8.82. All right, so we have 8.82. I'm trying to, my pencil is not working well today for some reason. 8.82 joule. There we go. Okay. I'm going to box this because I'm going to come back to it. Now, in position 2, right here, what's going on? Well, E2 is equal to K plus U, right? But what is the height here? Remember, U dependent on what? On height. Is there a height here? No height. So the potential is 0. Yes? So it's all 1/2 mv squared. And this v is what he's asking me to find. Okay? Now, so this is E2. But by the conservation law, E1 is equal to E2, correct? I can just equate them together. And in this case, this equation becomes 8.82 equals to 1/2 times the mass of the block, which is 2, times the velocity squared. and therefore I can find the velocity, which is the square root of 8.82, and then I would get the square root of that is 2.97 meters per second. And there we go. I have the velocity of the block. Got it? I hope so. All right, good. Let me do 27. 27 is kind of hard as well. I didn't want to do it today, but I'll do it. I'll do it quickly. That's on page 15. Page 215, that is. Right here. Okay? It says a 2.5 kilogram mass is pushed against a horizontal spring of force constant 25 Newton per centimeter. Watch that unit. Sneaky. Newton per centimeter, which makes it 2,500, right? Newton per meter. On a frictionless air table. The air table means what? No friction. The spring is attached to a tabletop, and the mass is not attached to the spring in any way. When the spring has been compressed enough to store 11.5 joule of potential energy. So this is the potential energy of the spring. Okay, the mass is suddenly released from rest. Aha. So that means what? There is no kinetic energy when the spring was compressed. Okay, that's fine. He said, find the greatest speed the mass reaches. When does this occur? B, what is the greatest acceleration of the mass, and when does it occur? Okay, all right. Piece of cake, right? All right, let's see how we do it. Again, a picture is worth 1,000 words, so I'm going to draw the picture. So here is, I'm going to draw 3 pictures of the spring. I just did this problem this morning to prepare this video lecture for you. Here is the spring. It's uncompressed, okay? Just sitting there, happy. Here is the mass away from it. And now what we do, you know what? I'm going to put the mass right there, but it's not compressed yet. So the mass is just barely touching it. So that's the kind of the position here. And then what I'm going to do, I'm going to push the mass against the spring. So now the second picture is the spring is compressed. Here is the spring compressed. And now the mass is right here, pushed against it. Got it? So now, starting from here, and now it is here. This is the compression. I'll just call it delta X. Call it whatever you like. Okay? And then the third is that I let the spring, or I let the, let's say that I'm putting my finger or my hand on this mat. Then I'll let go. What will happen? The block is going to shoot to the left like that. So now what you have, here is the spring, the good old spring. And then you have the block is flying off to the left like this. Trying to make it with motion like this. It's moving with some velocity v. You got it? Okay? That's the story. Now let's read the problem in light of this picture. Okay. First of all, he said the mass of that block is 2.5 kilogram. The spring constant, he said, is equal to 25 Newton per centimeter. Remember, the spring constant Newton per meter, so that makes it 2,500 Newton per meter. Okay, he's being sneaky here. He said, in this position right here, let's say this is position 1, 2, and 3. In position 2 right here, remember, it is at rest. So here is the block right there at rest. So it's being compressed. So the total energy here in 2 is equal to 11.5 joule, okay, of energy while compressed to the max. It's good. The spring is compressed to the max. You got that? Then you let go. What's going to happen? The block shoots to the left like that. Now all that energy has been converted into kinetic. Correct? Kinetic. All right. Now, question part A, he says, find the greatest speed at the moment of release. Basically, see, the mass reaches. Well, the greatest speed happened when? At the moment you let go of your hand and the spring, excuse me, the block is just leaving the spring. Here is a spring. Here's the spring, extends up to here, right there at this moment when the block is free of the spring. At that moment, it's the maximum. This is the maximum right there. That's the maximum velocity. Okay, so what's going on here? What's going on is the following. All that potential right here has been converted into kinetic. That's really what's going on. So maximum speed, max speed, happens when all potential energy, PE, converts to kinetic energy. See what I'm saying? So in other words, I'm going to take this potential and equate it to that new kinetic energy, because all that conversion happened, all that potential converted into kinetic, so that means all that potential is now all kinetic. I just call it K. Okay, so that means 11.5 joule is equal to 1/2 mv max squared. See what I'm saying? Now I can calculate the maximum velocity. Solving for v, so that's v max in this case is going to be equal to 2 times 11.5 divided by the mass under the root, and then we just calculate that. So that's 2 times 11.5. The mass is, what is it? 2.5 right there. 2.5 to the 1/2. Then I use my calculator for that. And that's equal to, I got 3.03 meters per second. There we go. That's the maximum speed. So when does it happen? At the moment of release. Okay? This one. See here, I said here, maximum speed happens when all potential energy converted to mass, or at moment of release. Assuming that moment of release is where the energy, all the energy converts. Okay? Got it? Okay. Part B. He says, what is the greatest acceleration of the mass when it does occur? Okay, the greatest acceleration. Well, in this case, we're talking about F equals ma. And of course, the F here is equal to kx. It's the Hooke's law. So equate them together, ma equals kx. And then the acceleration in this case will be kx over m, right? The only thing here is that what's not given to me is x. I need to find x. How do I find x? Well, based on what's given to me, see, he didn't give me how much compression. See that? Here is the block, and it's being compressed all the way up to here. He didn't give me this x. That's what x that I'm looking for. But he gives me something. He gave me the potential energy, and I know that. So what is x? So I know that u equals 1/2 kx squared. I can find x from here, because I already know this is equal to, what is it, 11.5, and then k is given to me, the k, and I just need to solve for x. You see what I'm saying? And when you do it, I'm not going to do it, you do it. When you do it, you're going to get x equal to 0.0959 meters. Okay? And then you just take that, plug it back in here to get the maximum acceleration. Okay? All right, one more problem, the last problem I want to do. I'm trying to finish the video before I push 2 hours because the system, I've learned, does not allow me to upload the program that I'm using does not allow me to upload any video that is more than 2 hours. So I always try to finish, hopefully, below 2 hours. Otherwise, I'm going to have to cut some. I have to do a lot of editing, which I don't want to do. So anyway, we have 15 minutes, so I hope we'll be able to do the last. I think I will be able to. I'm going to do the last problem that I want to work on is number 41, and this is also homework. Let's go over it quickly. Next page. 41 right here. He says a 25 kilogram child plays on a swing having support ropes that are 2.2 meters long. A friend pulls her back until the ropes are 42 degrees from the vertical and releases her from rest. Okay. What is the potential energy for the child just as she is released compared with the potential energy at the bottom of the swing? How fast will she be moving at the bottom of the swing? And how much work does the tension in the rope as the child swings from the initial position to the bottom? I'm going to have you do part C, okay? The work here. You could, well, I'm not going to give you a hint on it. When I was looking at this problem, I thought I'm going to give the student part C to work on it. So I'm not going to give you that one. All right, let's start and do part A and part B. So what I have, again, we're going to do a picture. Here's how the picture looks like. Basically, just going to draw something like a pendulum. It looks something like that. Here's the vertical. Here's the pendulum right here. The child and the swing and all that, and just a little block right there. And this is the angle theta. And of course, the pendulum or the child was here before it was pulled back. You see what I'm saying? So it has gained this much. So here is the swing right there. So it has gained this height. You see what I'm saying? That's the height the child gained. Remember, we're talking about potential energy, so the height is important. So that's the height. Okay. The length of the pendulum is L. He said that the L, or the swing, I like to call it pendulum. The length of the pendulum is 2.2 meters. The mass of the child in the swing and all that is 25 kilogram. And the angle theta is 42 degrees. And the initial velocity of the child right here is 0. Okay, so the initial velocity of the child is 0 before you let go. Okay, and now he's asking the question, forgot what he's asking for. Part A, what's the potential energy of the child as she is released? Okay, basically the potential energy while she's her parent is holding her before they let go, compared to the potential energy of the bottom. Okay, well, the bottom, you agree with me, is 0, right? Because this is the height right here. If I assume this is not the floor, let's just say our datum right here. This is height is 0, so that means the potential is 0. There is no gain in height here. You agree with me on that? So we want to calculate the potential right here. See what I'm saying? Well, the potential right there, this is part A, is basically mgh. H, of course, being this one. Okay? The reason I think this problem is hard is how do you calculate this h? Okay? Everything else is really not that bad. It's just this one. So I want to show you how to do that. Here is how it, and it requires a lot of geometry, geometry and trigonometry. Here's how it works. I'm going to draw it again. And that's general for any problem that you could see like that. So here is a vertical. Let's say that here is the swing. Here's the child again. We're going to make it into a little ball like that. And this is the length of the pendulum, right? The length of the pendulum, let's call it L. Now the pendulum is here. You know, it has swung like that. That's an arc. Okay, so this is the angle theta. So now look at this. If I take a line like that, this is L right here. Well, this length from here to here is what? If I can draw it better than that, I'll put it here. Sorry about that. That will be L cosine theta. You can pause the video and think about it, but this is L cosine theta. Why am I doing that? Well, I'm interested in the height right here, which is basically this one right here. Okay, this is the height. So that means the height is basically, here, look at the mouse, L, all of that, minus this much. See what I'm saying? All of that from here to here, minus from here to here. Got it? So it is L minus L cosine theta. So the height is L1 minus cosine theta. That's the height. It's a famous equation for the pendulum. You might want to keep it in mind if you see ever a swing or a pendulum. That's how you measure that height. Okay, so in this case, going back to my potential, so the potential here is mgl1 minus cosine theta. And that's it. Everything else is given to saying I have the mass of the child right here. I have the angle, I got the length, I got everything. So you can just basically calculate that. I'm going to have you do it yourself, okay? Now, for part, and then, so let me go back to the problem. He says, what's the potential energy for the child compared to the potential energy at the bottom of the swing? At the bottom of the swing, of course, the potential energy is 0 because there is really no height. Got it? Okay. Part B. How fast will she be moving at the bottom of the swing? Okay, so we want to know, now as the child comes down, we'll go back to the picture. So as the child comes down right from here, and it comes down, now she's going at a speed like that. Okay? So if I ask the question, what is the total energy here? Well, the total energy here is K plus U, but K is 0, correct? Started from rest. So all of it is just U, and we calculate, there it is, the U is right here. However, here, E equals K plus U, but the U is 0, right? Because here, there is no height. So it's all 1/2 mv squared. In other words, I could write it this way. mgl1 minus cosine theta equals to 1/2 mv squared. But I already gotten this number from part A. You remember? I got it right here, this number. So you don't need to do any algebra. Just put in that number in there. So you get that number equals 1/2 mv squared. And then you just solve for v. So v in this case will be 2 times that number divided by m under the root, and then there we go, you'll get the velocity. Okay? And I think I'm going to stop here. I've done enough problems. Please let me know if you have any questions. Have a good week. Bye.